Welcome to Scholars Academy. Let's look at a scenario. Imagine you start spending money, and the amount you spend doubles every single day. 10 rupees on day 1, 20 on day 2, 40 on day 3, and you keep this up for 12 days straight. This calendar grid tracks that daily doubling. To figure out the total amount you've spent by day 12, you could manually add all 12 numbers together. But as the days increase, the arithmetic becomes incredibly tedious. This is a visual breakdown of how we solve this faster: geometric progression. In our previous work with arithmetic progression, or AP, sequences grew by adding or subtracting a common difference. Here, GP sequences grow by multiplying or dividing by a constant number, known as the common ratio. Let's define the variables. The starting number is your first term, represented by the letter A. To find that multiplying factor, the common ratio R, simply divide the second term by the first term. To find any specific position in the sequence, you use the formula for the nth term, a times r to the power of n minus 1. We can also see a special property here. If three terms, a, b, and c, are in a GP, the middle term squared equals the product of the first and third terms. The first step in solving sequence problems is always identifying the mechanism. Once you prove a sequence multiplies instead of adds, you can use these GP formulas to compress weeks of manual calculation into a single equation. Let's apply this to a complex problem. This algebraic breakdown shows the search for the position, or n, of a negative fraction within a GP that has a negative common ratio of minus 1 by 2 by 3. Notice what happens to the negative sign in this specific step. When the power is an even number, like 4, a negative base yields the exact same positive result as a positive base. Because of this algebraic rule, we can rewrite the base to perfectly match the other side of the equation. Once the bases are identical, we drop them entirely and equate the exponents to find our position. Now we look at finding the total sum of a GP sequence. This formula sheet displays the two distinct equations for calculating the sum. The critical condition is the common ratio. You evaluate the absolute value of r. If it is greater than 1, you use the formula on the left. If it is less than 1, you use the formula on the right. Returning to our 12-day spending scenario, our ratio is 2. Since 2 is greater than 1, we select the first formula. We plug in our first term of 10, our ratio of 2, and an n value of 12. Evaluating this expression gives us 10 times 4,095, resulting in a total of 40,950 rupees spent over 12 days. Selecting the incorrect sum formula or failing to neutralize a negative exponent creates immediate calculation errors. These violate the specific algebraic rules that govern how geometric sequences compound. Let's examine a sequence using decimals. This visual shows the terms 0.3, 0.03, and so on. The safest computational method is to convert these decimals straight into fractions: 3/10, 3/100. By dividing the second term by the first, we derive a clean fractional common ratio of 1/10. Working with fractions makes evaluating large exponents much easier. When you reach the step requiring you to calculate 10 to the power of 8, you are dealing with a 1 followed by 8 zeros. Subtracting 1 from this gives you exactly 8 nines. You then apply the denominator to shift the decimal point exactly 8 spaces to the left, avoiding the risk of miscounting zeros in long division. Now, try this yourself. Given a GP sequence that ends in 32, find the 7th term from the end. Here is your hint. Figure out the total number of terms first. Pause the video now and solve it. Here is the breakdown. First, we use the nth term formula to find the position of 32, which reveals there are exactly 10 terms in the sequence. To find the 7th term from the end without writing out the whole series, use this formula: total terms minus the position from the end plus 1. 10 minus 7 plus 1 equals 4. You simply calculate the 4th term from the start. Board exams consistently feature sequences with decimals, high exponents, or reverse order questions. They design these problems specifically to filter out students who rely on rote memorization from those who grasp the underlying mechanical rules. Let's tackle a high-weightage competency-based board question. This problem asks us to find the value of p if the sum of the first 10 terms of a specific GP equals p times the quantity √3 to the power of 10 plus 3. We begin by setting up our standard sum formula and equating it to that expression. The denominator in our formula is an irrational number. To solve this, we rationalize it. We multiply both the numerator and denominator by the conjugate. This clears the roots from the bottom fraction, allowing the remaining terms to cancel out cleanly, isolating p and revealing a final value of 121. To consolidate, look at this final revision mind map. It connects the nth term formula to the two distinct sum conditions based on the value of r. It also shows the standard algebraic assumptions to use if a question asks you to find three unknown terms in a GP, a over r, a, and a times r, which ensures your r terms cancel out during multiplication. For maximum board marks, always write out the raw formula first to secure step marking. You must explicitly state whether your r is greater than or less than 1 before calculating a sum, and systematically double-check how even or odd powers affect your negative bases. Learning geometric progression gives you a reliable framework to calculate these rapid numerical changes. It provides the mathematical language necessary to track and predict compounding, exponential growth in real-world scenarios.